Hi everybody, this is lecture 13 and today I will tell you about line integrals, and this time is for real. Last time I thought last lecture I'd get to line integrals, but today I will start with them, so you'll definitely get to learn about them today. So let me emphasize, so today I will show you how to do a new kind of calculation, and our class, from now on will use these calculations all the time. So it's much better for you to learn how to do these things now than to learn, just before the second midterm. So let me just stress this. The homework for this section on line integrals, the homework for section 16.2, which is due this Friday, is the most important in the quarter, right? So you should do this homework extremely carefully and so you work a little bit now to save yourself work later. So you'll be able to follow the course much more easily if you do that, and then you'll have to study less on your own, and the lectures should be more self-sufficient. Okay, so let me tell you about line integrals. So we're going to be doing integrals over curves in the plane and in 3D space. I will start discussing, usually I'll start discussing the 2D case because that already contains the essential features, and it's easier to draw, and there's less letters to write. You just write x and y in terms of x instead of x, y, and z. Okay, so here are the axes, the x and y axes in the plane, and here's a curve. And I want to tell you what the integral over this curve C of a function of two variables is, right? So in 3D, if the curve lived in 3D, I would be integrating a function of positions in three-dimensional space. The curve is points in the curve live in 3D space. So, here they live in 2D, so I have a function of two variables. In 3D, I'd have three variables. So I want to tell you what it means to integrate a function. I want to tell you the definition of the integral of a function f over a curve C. So later we'll learn how to integrate vector fields over curves. So there are two kinds of integrals, two kinds of line integrals. We're starting with integrals of functions. So here's what I'll do. I'll just tell you the definition in terms of Riemann sums. That's how we think about this. That's how we relate this integral to applications. So I'll write this definition down, and then I will immediately tell you how we compute this in practice, how we set up this integral in practice. And for that, we'll need a parameterization. So first, the Riemann sums approach. So the Riemann sums approach is to defining this. So it's going to be the integral. So this integral is by definition a limit of Riemann sums. And to get a Riemann sum, you have to partition your curve into a bunch of little pieces. And then for each piece, so let's say I take 2 points in the curve. Here's the point coordinates. So the ith point with coordinates xi, ii, and here is the I plus first point with coordinates xi plus 1, yi plus 1. Okay, so so my formula is going to involve also the definition of the integral is going to involve the distance between these two consecutive points, and I will say the distance from xi, yi to the next point, that I'm going to call delta Si. So delta Si is this distance over here. Okay, so we're going to do a limit over Riemann sums, and here's the Riemann sum. So we're going to add over each piece in the subdivision the value of the function at the ith point multiplied by the length of the segment to the next point, multiplied by the distance to the next point, right? And then we are going to take the limit over all partitions. So we're going to take limits over partitions, over, subdivisions of the curve which are finer and finer and finer. So we're going to take the limit over all partitions where the distance between consecutive points go to 0 in some sense. So, but the essence is here. I don't want to delve into the abstract definition. Okay, so to emphasize, when we do an integral over a curve with respect to ds, so ds is called the arc length element, and what we're really doing is so the limit is approximately what you get by breaking up the curve into little pieces, and then you multiply the length of each little piece by the value of the function at a point in that piece, in here at one of the edges, and then you add over all the pieces, much like in 2D and 3D. So later I'll use this point of view to tell you what this integral is used for, but now let me give you the formulas that we'll use to evaluate this integral, right? So the Riemann sums approach, we almost never use it directly to actually evaluate the integral. So let me tell you how we're going to set this up in practice. And for that, we need a parameterization of the curve. So let's do that. Let's say we have a parameterization of the curve. So let's not underline it. So this means that I'm going to have a formula for points in the curve in terms of a single parameter t, right? So if you give me a number t, I'm going to give you, so this function, this vector valued function r of t is going to give me a point in the curve. And r of t has two components, x of t and y of t. And I'm going to parameterization also to be well defined. I need to bounds for t. So this means, so here's the t line, and we're looking at t values between a and b, and then r. So r, for example, so r of a is one of the two endpoints of the curve, possibly this one here on the left. So this would be r of a. This over here would be r of b. And if you give me an intermediate value of r, I'm going to get an intermediate value, intermediate point on the curve, right? So that's what a parameterization. This is a recap of what a parameterization is. For more details, please refer to the previous lecture. Now, so if we have a parameterization, right? So this means a formula for points in my curve. So formulas for the x and y coordinates of points in my curve in terms of a single parameter. If I have that, I can compute the line integral as an ordinary integral over the t line, right? So this pair of functions gives me a dictionary between points between b, numbers between a and b, and points in my curve, points on my curve. So it turns out it suffices to compute this integral. So we can compute the integral over c as an ordinary integral for t going from a to b. Then you evaluate the function f so if I have a number t between a and b, a real number t between a and b, I look at the corresponding point, the point in the curve corresponding to that number, that's x of t comma y of t. Then I evaluate the f at that point, and then instead of multiplying by dt, I really want ds, some distance in the curve. What I'm going to do is I'm going to multiply by a special square root that we saw last time. And then times dt. Okay, so this formula over here is the formula that we're going to use all the time to compute the integral of this function f over the curve c. Note that to write this formula, I absolutely need to have x and y in terms of a single parameter t, which I use to integrate. So I absolutely need to have a parameterization. Let me, say a few words to explain why this connects to that. So the idea is we're replacing a bunch of, so these sums over the curve, over these segments of the curve by an integral, which is really also given by Riemann sums, but the sums live in over segments, over little pieces of the t line, right? So what's going on here is that for each point points in the t-axis, the t-line give me points in the curve, but conversely, if you give me a point in the curve, there is a when you have a parameterization, you have a corresponding t parameter for that point, right? So here, let me call ti. Oh, I was drawing that in blue. So let me call ti the point in the t line corresponding to x, y, I, and ti plus 1, the point corresponding to xi plus 1, ti, yi plus 1, right? And delta ti is the difference, is the distance between these 2 points. So we saw last time that the distance, so the distance in the t line, so delta ti. So we really want to be adding the value of the function at the corresponding point. So if I give you a t, I want to evaluate f at the corresponding point and then multiply it by this length delta si. So all we have to know is what's the relationship between delta si and delta ti. And it turns out, as we saw last time, that delta si is a square root, something that looks like this, times delta ti. And that came from Pythagoras' theorem. That's why I have a square root and 2 squares. Okay, so one more thing I'd like to, so before we move on to calculations, I want to make an important point, 2 important points actually. So the first one is that we can write everything we see on this page using vector notation, and that perspective is often useful. So let's do that. Let's do that together. So I'm going to write everything using vector notation. I'm going to rewrite this integral using vector notation. So we have the integral for t going from a to b, and then we evaluate f at the point in the curve corresponding to this number t between a and b, to this parameter t. So r x of t comma y of t is, we've been calling that r of t. So let me just write that, r of t. And then I'm multiplying f at r of t by the square root of the components of, so let me see if you guys believe me. This is the length, so the square root is the length of the derivative of r times dt. Okay, can you see that? So r is just a pair of functions. When I say, so here I'm using a prime to denote the derivative. So r prime of t is, I could write that as dr dt, right? That would be fine. So we're looking, so let me be clear about that. So r prime is just dr dt, right? So this has components dx dt, comma dy dt. And then if I take the length of this velocity, of the parameterization, I get the square root that we had before. And then the dt was there. So you see I just rewrote the integral above using vector notation. And this is helpful because it gives us more perspective, right? So now it's clear. So here's an interesting thing. So if we imagine that the curve was the trajectory of a particle, and that r of t is the position of that particle at time t, then so I said before that the square root times dt was related to length on the curve, to distance between 2 points on the curve. And this, using the vector notation, becomes much clearer, right? So if we use our imagination give this parameterization a physical interpretation, then r prime of t is the velocity of the particle at time t. Then take the absolute value, get the speed of the particle at time t, and multiply that by dt. So its speed times a little bit of time gives you the distance that the particle moves in a little bit of time. And so this whole thing starts to look more plausible. The other point I'd like to make is that this whole discussion works in 3D as well, with very minor modifications. So in 3D, the parameterization. So let's see, there are a few things we'd have to change. So the parameterization would have a third function, z of t, right? X of t, comma y of t, comma z of t. The function would depend on z as well, right? So these points here, they would also have a zi component, zi plus 1 for the other point. And, but you can see that it's not hard to figure out where you should put the z's to make this, to get the 3D versions of everything, right? In the square root, you should add the derivative of z of t squared, and sure, so the derivative dr dt also has dz dt, so the velocity in 3D also gets a dz dt, also gets a third component. But notice that the vector valued, the notation, the formula that I wrote using vector notation, that works both in 2D and 3D. That's part of the beauty of vectors. So that's it. Okay, so that's enough of preparatory remarks. Let's just do an example of a line integral of a function over a curve. So the example will be, so we'll start, with something we already know how to parameterize, with our first example of a curve with parameterization, and that's a half circle. So the half circle, so we'll be doing an integral over the upper half of the circle of length 1, of radius 1. Okay, so that's our circle, C, that's our curve, and this is radius 1. And we want to integrate the function f of xy equals 2 plus x squared times y. Okay, so let's do it. So we're going to need a parameterization of the circle, but that's straightforward. So x of t, so x is going to be on this circle, x is cosine of the parameter t, y is the sine. Right, so to parameterize a curve is to give formulas for points in the curve. Explicit formulas that give you points in the curve, and this definitely does give me a point on this unit circle, and I also have to bound the parameters to just describe exactly the curve, the portion of the curve I like. So here I just want the upper half, so I'll just bound my parameters between 0. I'll just say t lives between 0 and 2 pi. I'm sorry, between 0 and pi, so I get the upper half. Now, with the parameterization and the function, we can just set up the integral. So the integral over c of f of xy times ds is, let me interrupt that for a second. So I just said ds, and I should emphasize that this square root times dt is the thing you put in place of the ds. So we had a ds before. So in practice, when you see a ds and you have a parameterization, you can freely substitute that by square root times dt. The square root over here times dt. Or alternatively, the length of the speed of the parameterization times dt. Okay, so let's set up the integral. So we're integrating t going from 0 to pi, right? So now it's an ordinary integral with respect to t. Then you evaluate, so you just plug in the parameterization into the function we're integrating. So that's 2 plus cosine squared t. So that's x squared times y. Y is sine of t. And then you multiply by that square root. So it's square root of dx dt squared. So the derivative of cosine is, so the derivative of x is derivative of cosine, that's minus sine, plus dy dt squared, that's derivative of cosine t squared. All this integrated with respect to dt. Now, you guys can see that the square root in this case, I chose this example for a reason. It's the computation itself is not, the integral is not going to be too painful. So here the square root just disappears again. So the thing inside the square root is 1. So that's square root is just 1. And then we're integrating 2 with respect to dt. That's 2t. The integral is 2t. The integral of cosine squared times sine, that's cosine cubed minus cosine cubed over 3. Right, so if I differentiate this term over here, the 3 drops, cancels with the 3, get cosine squared t, and then multiply by the derivative of cosine, that's minus sine. So I had this plus sign before, I just put in a minus sign to fix that. And then we evaluate this for t between 0 and pi, so that's 2 pi minus cosine of pi cubed, that's -1, then plus cosine, so cosine of 0 is 1, so 1/3. So that's 2 pi plus 2/3. So this number is the integral of this function here over c. So sometime, yeah, okay. So we can pause and be happy that we were able to successfully evaluate this integral. It's just a new process, and so getting the mechanics of this process ingrained and automatic is, I recommend, I think should be a top priority for you guys at the moment. So this is the mechanics of it. Now let me make a few remarks and explain what's the meaning of this number, right? So what did we calculate? What number is this? Or in other words, what are these integrals good for? What do they compute? So let's look at this. So the answer is we get all these applications we have for double and triple integrals. Let me just, before I go to there, let me just say this without you being distracted by the next slide. So all the applications we had for double and triple integrals, we can still do the same things with curves, with line integrals. The difference is that double integrals gave us information about flat shapes in the xy plane. Triple integrals gave us information about solids, allowed us to compute properties of solids in three-dimensional space. And now line integrals of functions are going to allow us to compute properties of curves in the plane and in 3D shape, in 3D space. For example, we can use, if we integrate the function 1 with respect to ds over a curve c, we just get the length of the curve, right? So let's see why. So if we look at the Riemann sums definition, we're subdividing, we're taking limits over Riemann sums. A Riemann sum you get by subdividing the curve into little pieces, so just did here. Then you multiply the length, the distance between two consecutive points, so by the value of the function. If I'm integrating 1, the value of the function is really not there, so I'm really just adding the lengths, these distances between two consecutive points, and in finer and finer subdivisions of the curve. So it's really giving me the length of the curve in the limit. So this is also, if this doesn't make a lot of sense, I encourage you to look at at lecture 12. So the next application, a very, very general application is, so if I have any function, so it's going to have a function of x and y. For each point in the plane, I'm going to get a number. Now, if I integrate my function, so this formula here is telling me that the integral of the function over a curve is going to be, so if I divide that by the length of the curve, right, L is the length of the curve, that's going to give me the average value of the function. So it's going to be some number between the minimum value that the function takes on the whole curve and the maximum value that the function takes on the whole curve. And the idea is that we're multiplying values of the function on this curve by and giving those values the weight, and the weight being on how much of the curve and what length of the curve the function takes that value. So the weight is, these values are weighted by arc length, the arc length of elements in the curve, the length of little pieces of the curve, and then you divide by the sum of all lengths, of all these weights. So the third application is to solid mechanics, to continuum mechanics. So if we have a density function for this curve, maybe the curve is made of a particular metal, or rather of different parts of the curve are made of different metals, then the amount of mass per unit length changes as you move on the curve. So if I have a function that tells me how much mass is in the unit of length at each point of the curve, I can compute, for example, the mass of the whole curve by multiplying the density times ds. So ds is the length of the little piece of the curve times the density gives me the mass of the little piece of the curve. If I add that over a subdivision of the curve, then I'm going to get, in the limit where the subdivision is really small, the mass of the whole curve. I can also compute, the center of mass of this curve. For example, the x-coordinate is this weighted average of the x-coordinates of all points in my curve. Now, so we take the x-coordinate of each point in the curve, and you give that the weight is the mass of a little piece of the curve. So rho times ds is the mass of a little piece of the curve, and at the end, you divide by the sum of all these weights. And finally, you can compute moment of inertia of the curve with respect to any axis. It's easiest to compute these moments around the coordinate axes. For example, the inertia about the y-axis is, so you just integrate over this curve the distance from the y-axis squared. So that's x squared plus z squared for any point in 3D space. And then you you multiply this by rho times ds and you add, right? Or just multiply this by rho and integrate with respect to ds. Recall, so the whole point in each of these three is that ds is the length. I should think of ds as the length of a little piece of the curve, and rho times ds is the mass of a little piece of the curve. Okay, so that's how we. So this is to. I hope this. So these first three examples are examples of serious calculations that we do with double integrals. Now, with line integrals. Now I'd like to show you a more, it's very visual, it's pretty, but it's less. It has to do with fence building, right? It has so it's useful for those of you who want to be fence engineers. But it's a very visual, very nice interpretation. It's the analog of the first thing I told you in the beginning of the course. When I recalled that the integral in one variable is just the area below the curve and below the graph. And in 2D, it's a volume below the graph. So in 2D, if we have a line integral, the line integral of a function is just the area. It's a certain area as well, but it's the area of a fence. So let's get that. Let's understand this. So here is so we have a function. So the plane and the function. So this is in 2D. So the curve and the function are well, the function depends on two variables, and the curve lives in the xy plane. So let me draw this curve. So this could be our curve. And now I introduced a new variable z because I want to look at the graph of the function f of x, y, but only over the curve c. Okay, so so for each point on this curve, I'm gonna see so the height here is gonna be the value of f at that point. So here's the idea. You're gonna get, if we draw the graph, if we look at the values of this function only over points in the curve, we're gonna get something that looks like this. Right, so in blue, I have the graph z equals f of x, y. So up top, you get z equals f of x, y. Just leave it, just leave it like that. Okay. Right, so if you give me a point x comma y, then the point on the graph has the same x and y, and then the height is f of x, y. And then, it turns out, so in 2D, it turns out that the integral is the line integral of a function f over this curve c is just the area of this fence. You know, the area below the graph of the function and above the curve c. And this is not that bad it even makes, I think, intuitive sense. So what's going on here is that we're breaking up our curve. So when we do the integral, we're really breaking up our curve into pieces, into little segments. So here I'm just drawing vertical lines above these segments. And then what we do is we multiply ds, so the distance between two segments, by f, which is the height at the height of, basically the height of this fence, very approximately, very close to the height of this rectangle. So f times ds just gives me the area of one of these rectangles, and then when I add all of them, and when I do the Riemann sum, I get the area of this fence in the end. Okay, so let's now discuss line integrals of vector fields. So I'd like to tell you next how we can integrate a vector field over a curve. So let me draw the curve so we can talk about it. So here's a curve, basically the same curve as before. Right, so there's our curve C, and so I'm drawing it in 2D because it's easier, so we can just focus on the concepts. And so we're going to be talking about the integral of a vector field over this curve. So we have a vector field. That's another ingredient for the integral. So I have a vector field f that'll have components p and q. Right. So p and q are functions of x and y. So this way, if you give me a point x comma y, if you give me a point in the plane, I evaluate those two functions at that point. I get two numbers. I think of that as an arrow. I think of those two numbers as a vector, and then this vector field, this pair PQ, is giving me a vector for each point in the plane. That's what we call a vector field. Okay, so we have a vector field and a curve. Oh, it's important. So for the definition that we're doing next for this integral, we need a curve plus an orientation, right? So I need a curve, and here I'm drawing it with a choice of the orientation that goes from left to right. The other possibility in this picture would be to go from right to left. So here I have so three ingredients for the integral: a curve, an orientation for the curve, and a vector field. So this is the thing we're defining: integral over C of f dot dr. So this is going to be a number. Just like the integral of a function was a number, the integral of a vector field over the curve is also a number. So that's what I want to tell you. And my approach to explaining this is the same as before. First, I will tell you so I'll give you the conceptual definition using Riemann sums, and then I'll write down the formula. So the conceptual definition is, so we're going to have a limit of sums, right? The sums will be, we'll have one sum for each possible subdivision of the curve. So here, let's say I have 2 points in, so let's say I choose let's fix a subdivision, just to explain what we're adding. Let's fix a subdivision of the curve. And now let me look at the, at this little vector here. Let's be more precise. So we have we have points xi, yi. That's the ith point in the subdivision of the curve, and then another point xi plus 1, yi plus 1, and delta ri is this little vector that points from xi plus 1, xi yi to xi plus 1, comma yi plus 1. All right, so here we have something slightly different than before. So before we were just considering the distance between the 2 points, but now we're looking at this vector that points from this point to the next, from one point to the next. And the relationship between delta Ri and delta Si is that delta Si is, maybe I'll put this as an observation here at the bottom. So delta Si is the length of delta Ri. Okay, so at this point xi, at the ith point, we have the vector that points to the next point in the subdivision of the curve, and we have also the value of the vector field at this point, right? So here, let me draw the value of the vector field like this. F at the point xi, yi. I have F, and we have this displacement vector. So delta Ri, I should emphasize, is just this position, the position of the ith plus first point minus the position of the ith point. So for each point, so we're doing a Riemann sum. So for each point in my subdivision, I'm going to multiply, do the dot product of F, the vector field, evaluated at the point x, y, yi, and then do the dot product of F with the displacement vector, delta Ri. Right, so this is, the dot product of two vectors is a number, so I get a number for each point here in my subdivision. I keep doing that for all of the points in the subdivision and add that. And it turns, so in the end, this limit for ordinary curves and ordinary vector fields, this is going to give me a finite number. This limit is going to give me a finite number because delta, if I choose, these points are really close together, really, if I have a lot of points and they're all cramped together, then delta Ri is getting smaller and smaller. So I'm adding more and more terms, but the terms are getting smaller and smaller. Okay, so this is how we define this. I will discuss. So this integral over here is called the work of f of the vector field f over the curve C. Right. So this terminology is definitely borrowed from physics, and I will discuss it at the beginning of next lecture. I will discuss, the interpretation of integrals of vector fields at the beginning of next lecture. Today I want to focus on how we compute this. So the work of f over c is this integral over here. Now let me tell you how we compute this. For that, to compute any of these integrals, to compute line integrals, we always need a parameterization of the curve. So let's say we have one. So parameterization, let's say for this curve, it's just r of t is x of t comma y of t. And t is between a and b. Okay, so we have a parameterization. Then if we have a parameterization, and I'm assuming that we do, then we can compute this line integral as an ordinary single integral. So we integrate t between a and b, and then we evaluate f. So for each number t between a and b, I get r of t, a point on my curve. So I'm going to evaluate f at the point on the curve that I get for that value of t between a and b. And then I'm going to do the dot product of that with the velocity vector of the parameterization. I'm going to do the dot product of that with dr dt. And then multiply by dt. So the idea, so the reason this works is that when you interpret the single integral as a Riemann sum, you're adding the vector field evaluated at points in the curve then you're taking the dot product of that with the velocity times dt, the velocity of the parameterization times dt. That just gives you that basically points. It's very, very close to delta Ri. It's basically pointing so delta Ri would be a secant to the curve C that very closely approximates the tangent. So it turns out this velocity times time basically gives you this displacement, the difference between the positions of the two vectors. So that's how we're going to compute this integral. Okay, so let me just show you. Let's do an example. So in this example, we're going to be integrating. We don't want to start too with unnecessarily complicated examples. So let me just take this vector field over here. Oh yeah, this is going to be a 3D example. So both the curve and the vector field will be in 3D. But we'll be applying this formula here, which is written in vector notation. So it works in 2D as well as it does in 3D. So that's our vector field. Has three components. So normally in 3D, the first two are called P and Q, and the third component is called R. So P, Q, and R are functions of X, Y, and Z. And then we're integrating this vector field over just a line segment. So our line segment is this curve over which you're integrating that vector field looks like this. So here's the X, Y, and Z axes. So this point over here is 2, 0, 0, and this point over here is 3, 4, 5. And we just want to integrate F over C. So before we do that, we need to parameterize this line segment. And so let's do that. So let's parameterize this line segment. Here's how we can parameterize. Here's a method that works for any line segment. If you have two points and you just want to parameterize the line segment joining the 2 points, you can always follow this method. So my function will be, so R of t will be the starting point, 2, 0, 0, the vector pointing to the starting point, plus t times the end point minus the starting point. Right? So I will, and the parameters, so the parameter will live between 0 and 1. So let's see, I'll write out this formula more, I'll expand this, simplify this in a moment, but first let's understand why this works. right? So my parameterization is supposed to always give me points. So R of t is supposed to, for every t, give me a point on this line. For every t between 0 and 1, give me a point in this line segment. So does this happen? So let's see. When t is 0, R of t is 2, 0, 0 plus 0 times some other stuff. That's 2, 0, 0. So when t is 0, I'm over here. When t is 1, okay, when t is 1, R of 1 is 2, 0, 0 plus 1 times endpoint minus 2, 0, 0. So I just get the endpoint when t is 1. And so, and as t increases between 0 and 1, the components, so the x, y, and z components of R of t, they increase, they change linearly, they interpolate linearly between these components. So you're really moving along this line and joining the 2 points. Okay, so now let's look at the, let me expand, write this parameterization in the way that we'll use it. So the x component of the parameterization is 2 plus t times 3 minus 2, that's 2 plus t, excuse me. And then the y component is t times 4 minus 0, that's 4t. And the z component is 0 plus t times 5, that's 5t. Right, so over here I have x in terms of t on this line, y in terms of t, and z in terms of t. And equipped with this parameterization, we're ready to compute this integral. So we're integrating, so we want to, let me move, how much room do I need? Yes, I think it's worth moving to the next page. So the integral over this curve, over this line segment of the vector field f, so here f is the vector field y, z, x. So the integral of y, z, x with respect to dr over the line segment c is, so we're integrating, we're doing an integral, this is an ordinary integral with respect to t between 0 and 1. So we're integrating t from 0 to 1. And then I'm going to express, let's look at the formula. So the integral of this vector field over C is the integral, this ordinary integral over T of the vector field F expressed in terms of T using the parameterization. So plug in the formulas for X, Y, and Z in the formula for F. So F is Y, Z, X. So Y, okay, it's worth doing this here. So F of R of T, in this case, so that's Y in terms of T. So Y is 4T. And then Z in terms of T, that's 5T. And then X in terms of T, that's 2 plus T. And the other thing we need is dr dt. So dr dt, so x is just 2 plus t, so dx dt is 1. Y is 4t, so dy dt is 4, and z is 5t, so dz dt is 5. And so we're doing the integral of 4t, 5t, 2 plus t. Right, so this is y, this is z, and this is x. And then we're integrating that multiplied by 1, 4, 5. And 1 is just dx dt. 4 is dy dt, and 5 is dz dt. Okay. So, and this is now an integral that we can definitely evaluate, right? So we're integrating between 0 and 1, 4t times 1, so that's 4t plus 5t times 4, that's 20t, plus 2 plus t times 5, that's 10 plus 5t. So this amounts to 29t plus 10, if I'm not mistaken. Actually, yeah, it's right. So it's 29t plus 10, and then when we integrate this with respect to t, I get 29t squared over 2 plus 10t evaluated between 0 and 1. That's 29 halves plus 10, which is 49 halves. So there you go. That's how we compute line integral, the line integral of a vector field. Okay, this I think is enough for today. So next lecture I will Okay, to close today's lecture, I'd like to show you another way, so how we can express the line integral of a vector field using component notation. And this is going to give us yet another way, so another way to write the same thing. The homework, the WebAssign, uses this other way. So instead of, WebAssign does not use vector notation as much, it often uses component notation. So let me show you how that looks like. So another, so let's do that. Another way to write the same thing. Right, so we were until now working with integrals of in vector notation. So this is the integral we were talking about. The integrals we were talking about, and but the vector field, the thing we integrate, is usually given to us as two functions of x and y. And here I'm doing the discussion in 2D, but in 3D you get exactly the same thing. So we're integrating this f, which really consists of two functions p and q, over this curve C. And the way we do this is we integrate t between a parameter t between two bounds a and b, and then we evaluate f. So we evaluate f at those bounds. I'll omit the evaluation. So this is f. F is just p and q, and then dr is dr dt times dt. Oops. Okay, actually, let me expand this even further. So dr dt is really dx dt comma dy dt. Then you multiply that by dt. Okay. So we can work out this dot product in general. So whenever, for any vector field in any curve, you'll always end up integrating a sum of two products, right? You'll be integrating between a and b, the limits for the parameter. You'll be integrating p times dx dt plus q times dy dt. And then you're integrating that with respect to dt. Right? I simply worked out this dot product. So here I did a calculation that once and for all, you don't have to repeat this. If you just want to say this is equal to that, you can just say that. And now I want to give you the new notation. So the new notation for the same integral. So here's new notation for the same thing. So this is the integral over c of p dx plus q dy.